Yeah, so let me just first thank the organizers for continuing this very nice conference every year. So actually I have changed the title of the talk. I wanted to talk about something where h bar is 0, but eventually I'm going to talk about something which is extremely quantum, which is entanglement. Okay, so it's entirely different talk, nothing to do with the other title. Okay, so that's what I'm going to talk about, but before I go there, so let me acknowledge the student who has done all the work, Animesh, who is a PhD student at IISc, and these details of this work you can find in this archive posting. Okay, so as the title suggests, I'm going to talk about localization. So let me just briefly mention what is localization and what is many-body localization in case you are not aware of or have not thought about it. So this whole idea, of course, started with Anderson in this very famous 1958 paper, and the basic idea was that if you have some quantum particle in some random media or wave in a random media, then what are the fate of the quantum states of the system? Okay, and so what Anderson considered is non-interacting electron, let's say, hopping on a random potential. So something like a tight binding model with some random on-site term which is drawn from some uniform distribution of disorder, and then what is showed that in principle there could be a completely different type of state which people have not thought about before him, which are called Anderson localized state, and moreover if you have very strong disorder, he showed that in a given band you can localize all states. Okay. And in that case these states will be exponentially localized in some region in space around some center R alpha with a localization length xi. And this is of course a non-interacting problem, you can completely diagonalize it and you write in terms of just a quadratic diagonal term where this will be the orthogonal states of the system. Okay, so it's a non-interacting system. Now what is many-body localization? So many-body localization is something also Anderson thought about, in fact that was the motivation of his 1958 paper. So he actually asked that if you put interaction among this system, among these electrons or these quantum particles, what happens? Now this question turned out to be extremely hard, and it took like last decade or so we have understood this question to some extent. And the idea is that you take interaction, put some generic, you take the electrons, put some generic interaction, something like this. What happens is just cutting the long story short, that what happens is that this interaction in principle connect all different single particle localized states. So there are matrix elements between them, and it's not obvious, and there are exponentially large number of matrix elements. So it's not obvious that the state will be localized. So the question of many-body localization is, can localization survive the presence of interaction? And the answer was given by this very famous paper by Basco, Alainer and Altshuler, and also similar time this one. And what they showed that yes, the answer is yes, and for sufficiently strong disorder you can have it. And just to summarize that the last decade of work, many people have contributed enormously to this body of work. What has emerged is somewhat deceptively simple looking phase diagram. What is drawn here is energy density in the y-axis. So this energy density is energy per particle or per site of a many-body system. So these are quantum energy of all the particles, not the single particle energy, and disorder on this axis. And what you find that there is in fact two types of phases. One is called the ergodic phase, which is the standard metallic delocalized phase, and you can have something which is analog of the single particle localization in the case of interacting system, which is called many-body localization, and there is a phase transition between them. Okay, there is some quantity which has been plotted here, and this is of course a generic thing, it's not related to this particular model I showed. You can ask this question in more or less any interacting disorder quantum model, like a spin model like this or Hubbard model, whatever you like. Okay, so this question still remains, it's not dependent on a particular model. Now, but there are many aspects of many-body localization. I'm just going to focus on one thing today. So the aspect is what is called the entanglement, which is the very nature of quantum system is encoded in entanglement. So in short, what you do is you look into a quantum state, you have a total system, you divide into two parts, A and B, and what you do, you trace out degrees of freedom of one part, and from a quantum state you generate a density matrix. Okay, so this is the reduced density matrix of, let's say, the subsystem A, which has a length or dimension, a linear dimension L. Okay, So now what you find in this many body localization transition, what happens is the very nature of entanglement changes from something which is called volume law entangled to area law entangled, and there is a very simple way to understand it. I will not go into it in detail, but what you can think that the whole system sort of forms arbitrary length Bell pairs, which gives you the entanglement, which is the volume law phase, which is the ergodic phase, whereas in the MBL phase these Bell pairs are only formed close to the boundary and which has an extent of localization length, and so you get a area law. Okay, so this transition is actually a transition from a volume law to area law, and this kind of transition we have never seen before in physics. Okay, and the reason is that so you can think that this entanglement is like a order parameter of this transition, and we still don't have a very good idea how to describe such transition. So this has started this whole paradigm of entanglement transitions and looking into models which gives you entanglement transitions. Okay, so now what I am going to ask today in the rest of the time, I will just go over the results very quickly, but the main question I will try to motivate. So what I am going to ask, that is to go beyond this kind of systems which are like a isolated system described by Hamiltonian. What I am going to consider is the systems which are driven systems, systems driven by some driving, let us say some voltage bias, let us say something like that. So you have this disordered system and you connect leads at the two ends. Okay, and so what we are going to ask, that is there a notion of entanglement even for such non-equilibrium steady state or driven system? Okay, can you still define entanglement and entanglement transitions? So of course we know a lot about this kind of thing, that if you put a small bias, that we know for the localized phase the current across the system will exponentially die out with the length of the system, and if you have a delocalized phase, it will be typically some power law of length. For example, if you have a ohmic transport, then this alpha, the exponent will be d minus 2. So the question that we are going to ask is that can the non-equilibrium steady state be characterized in terms of their entanglement properties? Is there a notion of entanglement even for such an open system which is connected to leads, and are there entanglement transitions like MBL transitions, okay, even in the non-equilibrium steady state setting? For example, what happens if you apply a large bias? Could you break down a many body localized state like you break down an insulator by like this Jenner breakdown if you apply too much electric or voltage, electric field or voltage bias? Okay, so now this question is very hard to answer and there are many technicalities here. So I am just going to discuss or show a toy model, and I will show why this toy model we discuss. So this toy model, I will not have time to justify why this toy model is used here that much, but this is the model. So what we want to look into is the model that I showed you earlier, which has this interaction and disorder. Now I have just changed this hopping term somewhat. So what I have essentially done is actually made this hopping term non-Hermitian. Okay, so I have added a imaginary vector potential, so which gives a asymmetric hopping. As a result, this is no longer a Hermitian Hamiltonian. You can ask that what is the meaning of Hamiltonian if it is not Hermitian, but this is, you can justify it from some open system formalism that you can have non-Hermitian description, effective non-Hermitian description of some open system. So what essentially happens in this way, that you can split this Hamiltonian into two parts, one Hermitian part and one part which is proportional to essentially the current operator. Okay, and if you make this lambda very large, you can see that there will be current in the state, because this the eigenstate of this current operator will contribute, and whereas in the other limit it will be the other state, and we have disordered here. Okay, so you can look also in a spin language thing here, and you can write a model. Okay, so now why this model? The reason this model we consider is because there is a history of this model. In the non-interacting case, it is called Hatano-Nelson model. So the main point of this model, so rather than putting a actual gauge potential, putting a imaginary gauge potential, is that it preserves time reversal symmetry. Okay, so now so your Hamiltonian has time reversal symmetry. However, since it's a non-Hermitian Hamiltonian, its eigenvalues could be imaginary, in principle complex. And as a result, even though the Hamiltonian has this time reversal symmetry, your eigenstate still can break this symmetry spontaneously. Okay, and what Hatano-Nelson showed, this is a plot of a single particle spectrum. What I have plotted here is the imaginary part of eigenvalues on the y axis, and in the x axis the real part of eigenvalues. what they show that even in one dimension in this model, in that case there is a transition from a delocalized state to delocalized state, and this delocalized state actually breaks time reversal symmetry and carries current. Okay, and this also defines a mobility edge from localization delocalization transition. So this model gives the opportunity to study a system where localization delocalization transition coincide with a symmetry breaking transition. Okay, so that is the question that we are going to ask, that in case of interaction, is it possible that you can describe a MBL transition by a symmetry breaking transition? Okay, entanglement transition by a symmetry breaking transition. So that's the question that we ask, and I will skip the detail, but so this is some, and we do exact diagonalization study of this model. What I have shown here is for a particular disorder realization, you can see that when you switch on this non-Hermitian term, you start generating, even in the interacting case, Hatano-Nelson was a non-interacting model, you can start generating imaginary part of many body eigenvalues. Okay, so I'll just discuss in the remaining 50 seconds, I'll just discuss the main results. So this is what I have shown here is the Hermitian case. So you can again look into this, I'll not go into the detail, but you can basically construct this phase diagram like I showed earlier. And in the Hermitian case, this is the diagram I showed you earlier. There is a transition from ergodic to MBL, which you can detect using entanglement or some other measures, not very important. So now you can ask what happened in the non-Hermitian case. Okay, so what you, and another, remember the question that we are asking in the non-interacting case, this localization delocalization transition is same as the symmetry breaking transition. Is this the case even in the presence of interaction? Okay, that's what we are asking. So what we find, just to summarize, what you find that in the interacting case, actually this localization transition, this entanglement transitions is actually separate or distinct from this time reversal breaking transition. So what is shown here is that let's say concentrate on these two phase boundaries. So this phase boundary is for the entanglement transition. So you get a volume law to area law entanglement. However, this time reversal symmetry is only broken at some higher disorder. Okay, so there is a region in between where you have area law phases, which actually also has some imaginary part of the eigenvalues. Okay, so this thing you cannot really describe this entanglement transition as a symmetry breaking transition, they become distinct, and again you can do standard finite size scaling etc. to analyze this transition and critical exponents. So and you can look into, you can define an order parameter for this time reversal breaking by counting how many imaginary eigenvalues you have, and that gives you this line. Okay, so so that's the main message. So I'll just show here. So now you can increase this non-Hermitian strength, and this is the Hermitian case which people have considered. And when you increase the non-Hermitian cases strength, you find that there is this two distinct transition. So what you find that indeed in a non-equilibrium static state, you can have entanglement transitions in this, and you can have current carrying state with volume law entanglement or area law entanglement. Okay, so that's the main message. However, this entanglement transition and T reversal breaking transitions, they are distinct in general, and so that's where I'll stop. Yeah, thanks.